the E2 reaction or the bimolecular elimination reaction. So in an elimination reaction, you're eliminating stuff from a molecule. In this case, we're losing a hydrogen from this carbon and a chlorine from this carbon. And so that's where the elimination comes from. And bimolecular refers to the fact that this reaction is concerted. So for the elimination reactions you're going to see in this chapter, almost all of them will be E2. This is your most common elimination mechanism for alkyl halides. So, most common elimination mechanism for alkyl halides. So this is what we will see. If you have to guess, if you see an elimination reactions taking place and you have to guess the pathway, guess E2. Don't guess E1, that one's pretty bare. Okay, so let's take a quick look at the mechanism. So we've got the alkyl halide. And so we can see where we're removing the hydrogen. So we're removing it from this carbon atom right here. And so in this reaction, so your hydroxide, if this was a substitution reaction, we would show it reacting with the electrophilic carbon. Instead, this hydroxide isn't doing that. It's not acting as a nucleophile. It's acting as a base and abstracting a hydrogen from the beta carbon. And it's forming a bond between the oxygen and the hydrogen. And these electrons are collapsing to form the pi bond. And then we are pushing out the leaving group. And that all takes place in one step. And so we have some important constraints on where this hydrogen is and where the leaving group is. So the beta hydrogen that you're removing must be 180 degrees away from the leaving group. So if we really wanted to represent that, so I can show on this one, so let's pretend this had some stereochemistry. Let's go ahead and draw in a wedge bond. So we have two hydrogen atoms on the beta carbon that we took a hydrogen from here. This one on a dash bond, that on a wedge, if you were to build a model and take a look at it, you'd see those are 180 degrees away from each other. So that would be the hydrogen that is being removed in this reaction. And so we can just see that a little bit better here. Okay, so that must be 180 degrees away from the leaving group. So the rate of this reaction, the bimolecular, it's still involving the nucleophile and the alkyl halide. So it involves both Rx and your base. Okay, substrates for an E2 reaction. So in the transition state, we looked at a transition state for the SN2 reaction, which is the bimolecular substitution. The transition state for the elimination, you have this partially forming double bond. And that's what really guides the substrate reactivity. So the more stable of an alkene you can form, the faster that reaction is going to be. And so more stable alkenes are more substituted. So tertiary alkyl halides react the fastest, and then secondary, and then primary. And of course, we leave methyl off this list because you need more than one carbon atom to form an alkene. So those react the fastest. And so if you have any kind of base with a tertiary alkyl halide, it's going to undergo the E2 elimination. And so that's why when we talked about the SM1 reaction, I made it a point to say that you needed to have a very, very weak nucleophile, very weak base. And that's because if you have anything basic at all, your tertiary alkyl halide will undergo an E2 reaction. So these are with stronger bases. Okay. And so when I did this reaction with the hydroxide, I took this hydrogen from this beta carbon rather than from the end in order to get the most substituted alkene that I possibly could. And I also deliberately took the one that would give me the transalkene and not the cisalkene, because we know that transalkenes are more stable than cisalkenes. So this tendency to take that the hydrogen from the more substituted beta carbon to give you that more substituted alkene, that happens when you have a smaller base. So smaller bases, things like hydroxide, methoxide, will give you the most substituted alkene product that you can form. And I say can form because you definitely have to have a hydrogen there that's 180 degrees away from the leaving group, or else it doesn't work. If you have a bulky base, so something with some steric hindrance, so the classic example of this is tert butoxide, right? Because we've got this oxygen with a negative charge and this carbon with all kinds of branching next door. So if you have a bulky base, you're not going to be able to get the most substituted alkene. This tends to give you the least substituted alkene, and that's because of steric hindrance, right? It's not the most stable alkene, it's just the only one that this base can form. Okay, temperature for an E2, like all elimination reactions, higher temperatures tend to favor E2, or any elimination, also E1 in the case of a very weak nucleophile. So higher temperatures favors elimination. And the solvent for an E2, we don't really have to worry about that in terms of a preference. You'll often see a solvent that is just the conjugate base of your nucleophile. So in this case, it's quite likely that the solvent would be water. So yeah, if you're trying to consider the reaction pathway for an E2, the big thing to determine E2 or E1 is that you have a base. So eliminations that occur under basic conditions are E2. So if you have basic conditions for your elimination reaction, it is an E2, right? So that means something like sodium hydroxide rather than water.